Let us start our today's lecture. Today, the topic of the lecture is reinforcement learning, some introduction to reinforcement learning. So this is one of the areas where application of deep neural networks has great benefits. Actually, using neural networks, you are currently able to solve some of the applied problems within the reinforcement learning scenario, but without neural networks, using only some simple transformation like linear functions, something like this, you are almost not able to solve any problem, any applied problem within reinforcement learning scenario. That is why we discussed this topic here in our overview course on deep learning. So, what is reinforcement learning setting? In a standard machine learning, let's start with this. In a standard supervised machine learning problems, we're usually having some data set, like a set of objects with inputs vectors x and with some target with some true answers y's. We first collect this data set somehow, then we introduce some, well, say, a score function that takes our x as an input. It has some parameters theta, and this score function allows us to predict our target variables for the input x. And also we introduce what's called a loss function, some function that somehow measure the difference between the true answer between true target variable and our score function f of x. And in order to learn the parameters theta here, we formulate the optimization problem of the following kind: a summation of all objects from the training set, our loss function on this training set, possibly plus some regularizer over parameter theta, and we minimize this with respect to our parameter theta. So here we suppose for efficiency of learning this problem that our score function f and our loss function L are actually smooth functions, so we are able to calculate the gradients of our L with respect to theta using usually automatic differentiation, and then apply some kind of stochastics gradient-based optimizer for solving this optimization problem. However, this formulation, supervised machine learning, may not be beneficial, may not be, well, natural for solving some applied problems of data analysis, so to say. So if we consider some applied problems, we may have problems in formulating, in transforming our applied problem into a machine learning supervised problem. A notable example here is actually playing a computer game. Suppose you're playing some computer game and you would like to learn a computer to play this game. For example, you're inventing some AI engine in order for it would be interesting for a human to play versus the computer in this for this particular computer game. So in the case of a computer game, what you have in time, you have the observation, which is just a screen of your game. So at each time moment, you're just looking at what's going on the screen. This is your observation. So some analog of this axis. And what about other things? First, about this training set, some collections of inputs and true outputs. In the case of a computer game, you do not have any reasonable training set. Why so? Because, well, you may in principle, you may measure how a particular person played this game. So save the collection of axes and what actions does he do at each time moment. But if he plays with versus some other opponent, some other human, depending on this opponent, our axis, our screen of the game actually changes. So even if you are able to learn, take all the situation for your recorded human performance and take particularly the same action as he does, it may not be beneficial depending on the opponent it plays with. So changing the opponent changes actually our environment, our set of axes. Next, it is quite clear that even with a recording of a particular human performance in a video game, you do not able to record all possible reasonable situation of screens in that particular computer game. So because there can be a huge set of configurations depending on the on your engine, on how you act in your environment, and that is why it is not possible to collect some fixed data set that what is called the representative data set that cover all good, all reasonable situations of a game in time. Next, what about the true answer here, the true target variable? In case of, say, image classification problem, we have the true answer. Given an image, it has some class label, and we know this label. But for the case of a computer game, so you do some action at each time moment. So what is the good action to do at this particular time moment? It is not clear. It is usually the case when starting from some particular position, you may do a different set of actions, and with this different set of actions actually achieve the same goal. So you do not have the notion of a right answer at each particular time moment in this case. So you actually not have any reasonable training set here. That is why it's difficult to tackle this problem as a machine learning problem. Then the next thing about the gradient-based optimization, about this loss function that we may differentiate with respect to theta. Again, for this example of computer game, what is your loss function? What is your measurable performance of your actions? It depends on the game. The only thing you have is that from time to time you have what is called a reinforcement, some value that you get. For example, when you win the game, you may get, say, +1, or if you lose the game, you may get -1 and have 0 reinforcement in all the other time moments. Or you may, well, if you are moving like Super Mario game, you're moving through the level, and if you collect some items, you may get points for this collection. And so from time to time, at some time moments, you get some rewards, some reinforcement, which is number of points that you collected this time moment. But in other time moments, you have just zero points. Nothing is going on. So for the case of computer game, your rewards, your measures of performance are actually a non-differentiable functions. So you are not allowed to directly use standard gradient-based optimization with respect to the parameters of your algorithm. So that is again one of the key difference of reinforcement learning scenario from machine learning scenario. So not having training data set, so you actually should collect your training data set during the training phase. Not having the right answers at each time moment, non-differentiable rewards, the delayed rewards, because you you need to make action in your game at this time moment, but the performance, the quality of this action will be measured only after some time horizon. So all these things are differences of what's called a reinforcement learning from machine learning scenario. Similar to the computer games, you may also consider another notable example of a situation when people usually try to solve the problem within reinforcement learning scenario. Is suppose that you control some robot. You have a robot that have a set of sensors, set of say engines, some controlling parameters, and you would like to learn how to move with your robot and possibly to reach some particular points in your map. So what you have, you measure by your sensors at each time moment the differences to all the walls in your map where you stay, and you at each time moment again you are able to make some actions like use this or that engine with a particular power, and your reward is your ability to, well, actually to move to reach some place in this map. So again, you do not have here a reasonable training set. You don't know the all good positions of your robots or good position of engines. You should just try this or that action and see what's going on. So you do not have a right answer at each time moment. You do not have a differentiable reward. So all the same things as we had for the case of computer games for considering this problem within a reinforcement learning scenario. And there are some other problems that may be tackled within RL. So now let's formally define what's going on in RL. In RL, we have, well, two notions. We have some agent that lives in some environment. And our environment is usually described by some vector S, which is called state of environment in a set of all possible states. For example, for the case of the computer games, this is just our screen, our image of a screen. This is a state of our environment. And we suppose that, for simplicity, that this state is fully observable, fully available by our agent at each time moment. For sure, this is not the general situation. It may be a case that agent is able to observe only a part of this state or some transformation of this state. This is the case which is called a partially observable environment. But for now, for simplicity, let's suppose that agent is for agent, the full state is available, and given this state, at each time moment, our agent make actions like move left, right, jump, shoot, depending on the environment and what is possible to do, doing some actions, some action A from the set of all possible actions, and so our agent make an action. And our environment with this action reacts in two ways. First, it transforms to some new state. Make a transition. So given a state S, given an action A that our agent make at this time moment, our environment moves to some new state S prime, and this is, well, this may be a deterministic function, or it may be probabilistic distribution, depending on the particular case, on the particular environment. So it moves to the next state, and also it gives to our agent a reward that depends on state and action. So these usually non-differentiable functions, like you're doing good or not. And also we should introduce here the policy of our agent. So our agent choose action A at particular state S using this pi of A given S. So this again can be a deterministic function, or it can be the probability distribution, and the same with the reward. The reward again can be a deterministic function or some sample from probability distribution. So this is the standard formulation in RL, which is called a Markov decision process. So if we run our agent within our environment, we can collect what is called a trajectory, tau. So we start from some state S0, the zero time moment. Then our agent make an action in this state, get a reward. And then our environment move to the next state. We make next action, get next reward, and so on and so forth till infinity in general case. So we collect this trajectory, and our probability distribution over this trajectory is determined by a Markov decision process, or MDP for short. Markov decision process, which can be graphically shown as follows. So, if we try to draw a kind of Bayesian neural network here, so we have our initial state as 0, then our action A0 is actually determined by our initial state, and our first reward R0 is determined by these two things. Then we go to the next state as 1, and this state depends on the previous state and the previous actions. Again, get a new action, get a new reward, and so on. So you see that in terms of S0, S1, S2, we have a Markov type chain. So our probability of ST plus 1 given all the previous trajectory, ST, AT, ST minus 1, AT minus 1, etc., is actually determined only, conditioned only on the previous S and A. So this is the Markov property. Okay, this is our situation, our agent moving within the environment, collecting some trajectory, and what we would like to learn here, what we would like to achieve. We collect what is called a cumulative reward, which is just a summation of rewards from every time moment, plus some what is called a discounting factor. So we consider the following series: summation from 0 to plus infinity, where gamma is some factor from 0 to 1 excluding 1. So this is our cumulative reward, big R, starting from time moment 0. And what we would like to do, we would like to maximize our reward, cumulative reward, with respect to all possible policies pi. So this is an expectation that is taken with respect to all the stochasticity in our MDP, with respect to this probability, or this probability, if they are probabilities at each time moment. So here we take an expectation of this thing, and we maximize it with respect to all possible policies in a set of all policies, trying to find the best possible policy that maximizes the cumulative reward in MDP. So why do people usually consider here a discounting factor? Why not just say that gamma is equal to 1 and not to use it at all? Actually, there are, well, two main reasons. First of all, if our series is an infinite series, so we have here summation till plus infinity, so we are living in our environment for infinite time moments. Without discounting factor, we just do not have here some bounded value. So our rewards, immediate rewards, are usually taking values from a bounded set, like from -1 to +1, for example. And without this gamma, the summation till plus infinity would finish with a plus infinity value. So in order to have a convergent series here, we need to add some discounting factor. That is one reason. The other reason is that even if we consider some finite time horizon scenario, so this summation goes not till infinity, but some fixed time moment, it may be beneficial to introduce the discounting factor that, for example, suppose you're working with this robot example, so you're moving with your robot to some particular position, and your rewards are 0 everywhere, and you get +1 if you reach the right position. So if you do not use any discounting factors, we use two situations have the same cumulative reward. The first situation, you're just going straight to your desired goal. And the second situation is you're moving forward and backward for some time moments, and then moving directly to your goal. If you do not have any discounting factor here, so you always collect zeros, and +1 at the end, so there is, well, no difference between these two situations. However, in practice, you would like to achieve your goal as fast as you can. And in case you introduce this gamma factor here, it would be beneficial for a robot to reach your goal as fast as he can. So it would be more good with respect to this cumulative reward to go directly to the goal and not to move forward and backward for some period of time. And with this gamma, you're able to control what is called how your agent in making decision, how it looks to the forward in time. So if your gamma is close to 0, it means that making a decision at a particular time moment, your agent is actually looking to the current reward and possibly only to a few neighboring rewards. So it's consider only a few time horizon, foreseen time horizon in making actions. If your gamma going to 1, making closer to 1, your agent in making action at this time moment and trying to understand, to foresee what would going on in a long time horizon. So it is more reasonable agent, more clever with respect to the time. That is why people usually add this gamma, and this gamma is a hyperparameter, so it's something that you choose by itself and put with the environment that you learn. Okay, so this is the formulation of a problem. You have these rewards, this gamma, and you would like to somehow learn the optimal policy in this MDP. And now we are going to consider some particular algorithms, how we actually are able to learn the optimal policy. And in reinforcement learning, there exist a numerous number of approaches. So we start with the most simplest one, and then so the next lecture we'll speak about more advanced techniques. So first, let's discuss the situation when we are able to learn the optimal policy directly. So we are guaranteed that we, in some particular situation, that we are able to learn the true optimal policy in MDP. So this is what is called the value iteration algorithm. Value iteration that we now consider. Since we have something like a Markov chain here, and we are looking for something like an optimal configuration of actions in this Markov chain. For those who are familiar with, for example, with hidden Markov models, you know that optimal configuration of actions at each time moment is usually determined by a type of dynamic programming algorithm. And in dynamic programming, you usually introduce some kind of a Bellman, what is called the Bellman function. That shows you the optimal performance starting from a particular time moment, what you're able to get in the optimal trajectory. And this Bellman function is usually denoted by a V function. That is how the Bellman denoted it in his articles on the dynamic programming algorithm. So here in value iteration, we are going to introduce something similar to the Bellman function, which again would be denoted as V function. And this function would depend on some state S and on some particular policy pi. And this value function is defined in the following way. So here we have we start with some particular state S at time moment t. Then, starting with from a particular position, we are collecting a trajectory using our particular policy pi. This big RT, this is a cumulative reward that we get from our environment starting from the moment t, and we get an expectation with respect to all stochasticity within our MDP. So this is just our cumulative expectation of our cumulative reward if we start from a particular state in our environment and choosing actions according to our particular policy pi. Note that on the right here, we have some expression that depends on the time moment t, and on the left, we have expression that do not depend on t. So we do not put here index t here. Why so? This is because of summation till infinity here. So since we consider an infinite time horizon and our Markov decision process is what is called a homogeneous. So all these probabilities that are stated here, they are not depend on the time moment. So we do not have, say, index t here or here or here. It depends only on a particular state and action at this time moment. So this is a homogeneous Markov decision process, and that is why there's no difference the starting time moment that we get here. So we are counting till plus infinity. We are working with a homogeneous Markov decision process. So this expression actually does not depend on particular t, on particular time moment from which we start. That is why we do not have index t here. So this is the, well, what is called the value function, or Bellman function, if you like. And this value function is formulated for a particular policy pi, and we are interested in optimal policy, and that is why we may introduce the V star, which is just a maximization of all possible policies of our V function, this state S. So here this is the best possible value function for the best possible policy pi. And occasionally, the algorithm we are going to discuss now is the algorithm that would try to learn not our policy pi directly, but instead learn this value function, this optimal value function for each possible state in our environment. So there will be an algorithm that first learn this optimal value function V star, and then having learned this function, it is able to extract actually the optimal policy pi. So let's discuss how this algorithm is organized. So first of all, again, let's rewrite our cumulative reward. This is some discounted reward, plus etc. And we may rewrite it in the following way, like move our gamma out of the brackets and say that this is a gamma multiplied by 1 plus gamma f2, gamma squared f3, etc. And what is stated here is actually capital R1. So this is the cumulative reward that we get starting from the first time moment. So here we have a kind of a recursive formula that connects the cumulative rewards at the neighboring time moments. And this is, by the way, the reason why we are introducing the discounting factor in this particular way, like using a geometric series. So in principle, it is possible to consider here arbitrary monotonic decreasing function in time. So we should somehow account for that getting a reward at the next time moment is worse than getting the same reward at this time. So any monotonic decreasing function would fit to our desired properties. But if we choose this discounting using geometric series, we are able, actually, the main benefit that we are able to have this recursive expression connecting the cumulative rewards and neighboring time moments. Okay, so now let's start with our optimal function, which is a maximization of all possible policies. Next, suppose for simplicity, again, for now, that we are working only with deterministic strategies. So these pies are actually not a distribution of actions, but just some deterministic functions. So it shows us the particular action given some state. So this is a maximization over deterministic functions. And we say that, we may say that this is less than equal to a maximization over actions at each time moment. So A0, A1, A2, etc. So here we consider the maximization of over all possible actions that we may choose at each time moment independently of what? Of our V function with these actions depending on S. Why we have a less than equal sign here and not just equality sign? How do you think? Why maximization with respect to all possible deterministic policies here is actually less than equal than this maximum?
Because it can be much broader than optimization over policies.
Why?
Because policy constrain how they take different A's. And if we optimize without regard to this constraint, then it's broader.
Well, yes. In policy, we have some kind of a consistency. So our policies say that at the same state, we should choose the same action, regardless of the particular time moment at which we observe this particular state. So here, in this maximization, we are choosing the same actions for the same states. But here, where, at least in theory, we are allowed to use different actions for the same states at different time moments. The question. R0 is a starting reward, and we accumulate reward with information about next rewards. Didn't get the questions. So why we have some abuse in notation? So our small are intermediate, are our immediate reward at each time moment, 0, 1, 2, etc. And this reward R0 depends only on state and action at this time moment. So R0 is actually a function that depends on state and action at the same time moment. And this is true for all the other rewards. Why do we have some abuse notation here? Okay, so let's move forward. So we have here this maximization. Now we put our expression for V. So this is a maximization of actions. What is V? This is our reward at the first time moment, plus gamma, then expectation with respect to the transition probability on the first time moment as prime given S and A0, then goes expectation with all the remaining stochasticity and MDP, and here states the cumulative reward. So R1 with S1 starting from S prime. So here I have used actually this recurrent formula and add an expectation because our V function is actually an expectation of a cumulative reward. Okay, so we have a max over all possible actions, and here the sum of two terms. So the first term depends only on the A0. It means that we may move a maximization over all other actions starting from A1, A2, etc. inside the expectation using the distribution property of a max and sum operations. So we may write that this is actually a maximization over A0 of this reward plus gamma. And the maximization, A1, A2, etc., expectation, like this. So here we moved an maximization of all next action inside these expectations. And then what we have here, this is actually this thing. The optimal V function starting from the state S prime. The only thing is that everything is started not from zero index, but from first time moment. So that is the same thing. So this means that finally we got the, yes, this is the, the V function and what is the optimal action. It's important, the optimal action.
Wait, can you comment about the function? The function was maximum over P's strategies, but here we have a broader set.
Yes, agree. So what I'm trying to prove now is that actually here we do not have an inequality sign, and this is actually an equality thing. So the true maximum over all possible actions is is reached only on a consistency policies. So you are not able actually in this maximum to choose different actions in the same states. That is what I'm going to prove now. So for now, you may think that this is not the this V function, but this is a V function that is formulated in terms of independent actions. And taking this into account, our optimal A0 would be what? Would be argmax over actions, our immediate reward, plus gamma, transition probability, and well, this, say, modified V function, the maximization of independent actions. And you may note that this expression does not depend on the time moment. So this is a function that depends on what? It depends on S, and that's all. So we do not have a T index anywhere. So this is actually our optimal policy pi of A given S. So if we fixed some particular state S, our optimal action would be the same regardless the time moment we consider here. So that is why this inequality is actually an equality, and our optimal V function is actually, we may write that this V star is actually this one, where maximization goes with respect to consistent policies. So again, we may write down the following, what is called the Bellman equation for optimal policies, that the optimal V star is a max over actions plus gamma, transition probability, V star S prime, and this is true for all states, and our optimal policy pi is actually argmax over A over actions from the same expression. So this is our result, and moreover, here I said, well, that for simplicity reason, let's consider only the deterministic strategies. Even in a more general case, when we consider all possible strategies, including some probability distributions over actions, the result would be the same. So the optimal policy would always be a deterministic policy, even in the case if you allow yourself to consider some probabilistic policies pi. So this would be the optimal policy for any MDPs. Okay, so we have this result. This is called the, for V function, the Bellman equation, which is just some recursive expression for V function. And now we are going to learn this actually function for in the most simple case when we have just a discrete set of actions and discrete set of possible states. So we consider that this maximization is is actually maximization over discrete set, and this expectation over S is again is a summation of all possible states, which is, well, a reasonable number of possible states in our environment. Okay, and what is written here? So in the case of the of discrete environments, our V function, V star of S, is just a vector of numbers. So this is the values of V function for all possible states. And here we have an expression of the following form. Some V function, V star, is actually some transformation F on V star. And this F is this maximization, etc. What kind of transformation is this function? Can you say, can somebody say, what is the type of this function F? Is it, I don't know, non-linear function? What kind of transformation we have here? For the case of discrete environment. Okay, does anybody see that that this system is actually a linear system over V star? So it is just a set of linear equations.
But don't we have a maximum?
Yes, we have maximum, no?
Yes, agree. So if, because of the max, we do not have exactly a linear transform, because we have a max over some linear transformation over V star. So because of this expectation, here goes a summation over S, so, S prime. So here this is just a linear transform plus a max, agree. So this is not a linear system, but anyway, we see that our optimal V star is a fixed point of this transformation. So our optimal V correspond to this equation, and in the case of this F being a contraction, we may say that our V star is a unique point, and we are able to find this point using a fixed point iteration. So we may consider the algorithm of the following form: initialize somehow our V, and then make iteration of the following form. And if our F is contraction, that this algorithm would guarantee to converge to the true fixed point, which is unique, and this is our optimal V star. And this is the case. So even with this max, it is possible to prove that our F is actually a contraction, and our final algorithm, which is called a value iteration here, is the algorithm of the following form: V nu S is the max over actions plus gamma V old first prime. So what we do, we organize some kind of a circle over all possible states in our environment, and within this circle we making the calculations of the following form, given the old value of V, calculate the new value till convergence. And in this way, we are guaranteed to, if we are able actually to calculate what is written here, meaning that if we are able to calculate these expectations and take this max with respect to all possible actions. If we are able to do so, we are guaranteed to converge to an optimal Bellman function, value function. And from this optimal value function, using this formula, we extract the optimal policy pi. That is the algorithm that is called a value iteration. Let's consider some simple example on how it actually works. Consider the following simple map. Something like this. So this is some field, and our agent is moving in this field, moving left, right, up, and down. And our rewards actually depends only on the position of our agent, and it is 0 everywhere. 1 here and -1 here, and this thing corresponds to terminal states. So our state is actually position of an agent in this field. Our reward depends only on state, and it is shown here. So, and our actions are actions like move up, down, left, right. And we would like to learn the optimal policy and what the optimal policy here looks like. So we start from some arbitrary position in this field, and our optimal policy is the shortest path to this +1 state, to +1 position. This would be the optimal strategy here. And let's apply our value iteration algorithm for that particular case. So in the first time moment, we initialize our v function, which is at the first time moment, our v function is reasonable to initialize it with a reward function, with immediate rewards. And then let's recalculate this v function using our particular algorithm. This algorithm for sure depends on a particular order that we use to go through our field. So let's fix some order. Suppose we go, for example, in these directions. It doesn't matter. The algorithm is guaranteed to converge with any order that you choose. Suppose that you recalculate the values in this sequence. So having v0, we would like to calculate v1. Here are two terminal states. It means that for sure our v function is always equal to reward in this terminal states, because we are not reaching this position. We are not able to move anywhere. So our v will be -1 and +1 here. And now we are recalculating our v in all the other positions. So we are stating here and this point, and we trying to calculate this value. So take a max over all possible actions. In this situation, we are able to move upwards and to the left, and choose a max between these two values. So if we are moving upwards, we got our reward in our current state, and our reward here is 0. Here our rewards, and then we move upwards, and we got 0 plus gamma times v function at the new position, and the v function at new position is -1. So if we go upward, we get minus gamma here, and if we go to the left, we got 0, because this would be 0 plus gamma multiplied by 0. So a maximum between these two values, 0 and minus gamma, would be 0. Next, we go here, consider this position. Here we have three possible actions, upwards, left, and right. But regardless the action, we always have 0 everywhere, etc. So we're going in this sequence till that place. And in this place, we're stating here, and if we go to the right, we are able to get a gamma plus gamma, because we got here 0 plus gamma times 1. So that is why the v function would be gamma. And then if we go here and again take a max, the optimal thing would be gamma squared, because if we are stating here and go upwards, we got 0 plus gamma multiplied by what is stated here, gamma. Again, so this is gamma squared. This is our v1 function after the first iteration, after the first cycle of all possible states in our algorithm, in our value iteration algorithm. Then v2. One minus 1. Again, 0 here. Now, here we already have gamma squared because we may go upwards and use this value, gamma squared times gamma. Then go here, gamma the power of 4, 5, 6, 7. Then at this position, we looking left and right. To the left, we got gamma at 8th power, and to the right, gamma at the 2nd power. So this is the gamma squared, gamma squared. V2, then we, on the third iteration, now we have here gamma at the power of 4, because we have gamma squared, gamma cubed here. So this is. Now we propagate this gamma here to the right, so gamma cubed squared y minus 1, and the fourth iteration would be the last one. Now gamma the power of 4, we propagate here gamma cubed. So, and this is equal to the optimal v function. So our optimal value function at each particular position show us actually the length of the optimal path to the right upper corner. So starting here, in order to reach this position, we need to go through 5 cells. That is why here we have gamma in the power of 5, and the same for all the other points. And together with estimating the optimal v function, we also estimate the optimal policy, saving the argmax on each recalculation. So we know in this recalculation that at each particular position, for example, if we stay here, we should go to the right and not to the left, and in order to have the optimal action. And for that particular item, there are 2 optimal trajectories. If we start from here, we may go in this way, or we may go in this way. These 2 ways actually have the same values, but the trajectories is different, and depending on the order you recalculate this argmax, your algorithm would choose either this or that trajectory. So this is the the value iteration algorithm, and again, this is the optimal algorithm in MDP. So if you are, for some reason, able to apply this algorithm, this is the best thing you may do. So you don't need to consider any other techniques. However, the problem here is that in almost all practical situations, you are not able to apply this value iteration algorithm. Why so? This is because of several reasons, and the main reason here is that in real environments, you usually do not have access to this transition probability because as a function. Because what is the transition probability? For example, for the case with computer game. So you should know, taking a screen at a particular time moment and some action from your agent, what would be the screen of the game at the next time moment? So you should model this screen changing. And for sure, this is something that is very difficult to learn. This is a very difficult transformation. And that is why you don't know this function as some deterministic or realistic function. So you are able, at a particular state, to make an action, and to at a particular state, you make an action and look at the next state. So this is easy to get, but to make a forecast here, to make it this probability as a function, this is something that you do not have an access to. And even if you have, even if you know this probability, next you should calculate an expectation over all possible states in your environment. And for the case of a screen of a game, it means that you should make a summation of all possible pixel configurations for the image of a particular size. So this would be a huge sum, and this is something that you actually are not able to do in practice. Next, the next problem is our V function for each possible state. Again, if you have a discrete case and number of states, well, is not very, very big, like here we have how many? 8, 11 possible states, 11 possible positions in this board. So here you have not a lot of states. It would, in this case, it would be a small vector, and it's easy to recalculate it. However, for the case of the game, again, you should allocate in the memory a vector of the size of all possible input images of a game, so all possible configuration of pixels for image of a fixed size. So it would be a huge vector that you, in practice, are not able to save in memory and somehow recalculate. So you're not able to save this as a vector. You do not have access to this function to transition probability. You are not able to calculate an expectation here. And concerning this maximization, again, it depends on how many actions you actually have in your environment. In the case of a game, usually there is not a lot of actions, like moving left, right, doing something, some fixed set of actions. But in some other situations, for example, for the case of recommender systems. In recommender systems, at each time moment, your possible actions is a set of items that you would like to recommend to your user, to a user. And this means that a set of possible actions is a set of all possible configurations of, say, 5 items among all the items that you have in collection. So it would be a combinatorial number of possible results, and calculating a maximization with respect to this huge discrete set for sure would not be efficient. You are not able to maximize just in a loop all possible actions. So in real situation, many of the components in this formula, you're just not able to calculate. And that is why in practice, we need some different algorithm, not the value iteration algorithm. And we now are going to discuss a couple of these algorithms that try to solve this or that restriction of the value iteration. Let's first somehow cope with the main restriction, that we do not have an access to this transition probability in the real environment. So in real environments, we are able to do what is called a trial and error method. So you're just able to make actions in the environment and look at particular states that you're reaching. So you just at some state, so it means that you are able to sample from this distribution. So taking some state, you make some action and see what S prime you get from the environment. So you are able to sample from this distribution. And now we will discuss a kind of a value iteration algorithm, but for the case when we sample these three things, states, action, and the next state. And this algorithm is usually called what is called a Q-learning. So now discuss this one. This algorithm in its structure is actually quite similar to what we had in the value iteration algorithm. Again, we are going to introduce some value function and consider the recalculation, this value function in iterations. And in this case, we would introduce the following function, Q. Q states for quality function that is now depends on two things, on the state, on the current state of our environment, and the particular action that we are making in this particular set. And again, we constrain on particular policy pi here. So this is an expectation of our cumulative reward, starting with a particular state, as making a particular action. So at the time moment t, we are stay at state s, we are making action, this particular one, that is argument of the function, and on all the next time moments, we are choosing actions according to this policy and make an expectation of our cumulative reward. So this is a Q function, quality function. This quality function is defined for a particular policy pi. Similar to the case of V function, we may introduce the optimal Q function, which is a max over all possible policies, our Q functions, like this. And then having this notion, we again may find a kind of a Bellman equation for the optimal Q function. So for the Q function, I'm not going to, this is absolutely the same thing as we have for the case of optimal V function. So the optimal Q is our reward at this time moment plus gamma, transition probability to the next state. And here we have a max over the action at the next time moment, our optimal Q function here. So, and this is true for all possible states and action. So this is the Bellman equation for the optimal Q function. And if we somehow learn this Q star, then it's easy to extract the optimal policy pi. The optimal policy will be just argmax over action, our optimal Q function. So our Q functions say that depending on the action, the quality of this action would be the value of this function. So it means that at a particular state, we should choose the action with the best quality. So taking an argmax with respect to action for the optimal cost. Okay, so now we say that we are not able to calculate this expectation directly. We do not have an access to the to this probability distribution, but instead we are able to somehow sample from this distribution. And how to solve this Bellman equation in the case of sampling. And usually people do the following thing. Let's transform this problem into a regression-like problem. So we say that since we consider the discrete case, the case of discrete set of states and set of actions, we may consider the following criterion function, a summation over all possible states and actions. And here states a difference between Q and what is written here. Squared, and we minimize this with respect to Q star. So here we have a set of nonlinear equations. Q star is equal to some function that depends on Q star. And we transform it to a mean squared error problem. We say that what is written here is some kind of a target minus y SA. And we would like to make this to same Q star at a particular state and action close to this target for all possible states and action. So this is an equivalent transformation. And what we do next, since we are able to sample from a set of state and action, we are just apply a stochastic gradient step. So we just apply SGD here. So at a particular time moment, we sample a mini batch of state and actions. In the simplest case, just one object. So we sample state, action. Then making these actions, we get some reward and go to the next state as prime. So sampling this thing, we modify our function to nu of SA is equal to old minus, because we're minimizing, some step size from the gradient descent times what? Times the stochastic gradient from our criterion, and this stochastic gradient would be equal to u old SA minus target like this. Yes. So here we suppose that our target value is actually does not depend on the Q function at a particular moment. So what we do, we say that having the current estimate of our Q function, we estimate our target variables, these y's for SA. Then we make some set of steps from our optimizer, possibly one step or many steps. So trying to make our next estimate for the Q function closer to these target variables. So we make some set of steps, then recalculate our target variables, these y's for S, and they again make some set of stochastic iteration, etc. And it is possible to prove that we are guaranteed with this algorithm to converge to the optimal Q star function, even with this sampling procedure, with some requirements on this sampling. This sampling should be organized in such a way that I actually try all possible state and actions in your environment. So let's a bit transform this thing. So it was 1 minus alpha q old, let's say, plus alpha y s as a. So it's a kind of exponential averaging. So this is our algorithm. And as you may know, this algorithm now do not depend on actual knowledge of this transition probability, and it doesn't require you, even if you know this, to calculate any expectation. You just using samples, and with these samples you learn the optimal Q function. Note that the absolutely the same type of algorithm it is possible to formulate also for the case of V functions, because again, if we come to the V function, again, we have here some set of nonlinear equation that V function is equal to some function that depends on V. We may solve this Bellman equation in a similar regression type manner. So say that this is our targets, and consider mean squared error criterion function and minimize it with respect to V star, making a samples for each state and action. So it is possible to organize similar algorithm also for V function as well. However, in practice, people usually do it for the Q function. Why so? This is because of the place of a maximization with respect to actions. For the case of V functions, in order to calculate our target for a particular state S, we need to make all possible actions, to try actually all possible actions A in our environment, get some U states S prime, and do this maximization. On the contrary, for the case of Q functions, here, when you calculate the target value, if you fix some state S, if you stay here, you do not need to make all possible actions in this particular state. You already have just one action A here. You have the next state S prime, and you take a maximization of all actions for some fixed function Q here. So you're not making action in a real environment, you're just making a maximization of a function that you know. For all reinforcement learning scenario, we assume that the most difficult part is interacting of our agent with environment. So making an actions in environment, some states, and collecting the next state is the most difficult part, because it requires you, well, the real engine. If it is a robot, you need to move your robot to the next time moment, so you make a physical movement. Or if you play with a game, in computer game, so you should run this engine for a computer game that would calculate the screen at the next time moment. So it's a difficult part in terms of time. That is why applying this type of algorithm for the Q function is much better, is much more efficient than using the same algorithm for the V function. That is why we have the algorithm that is called the Q learning. So it learns the Q function. Okay. And one more thing that we now should say about this sampling procedure, that I said that in order these algorithms to be convergent, we should organize the sampling procedure well in a proper way. So we should somehow try all possible states, or many possible states in our environment, and many possible actions for each possible state. And that is what is called in reinforcement learning so-called exploration-exploitation dilemma. Exploration-Exploitation Dilemma. What is it? In case of the value iteration algorithm, in our environment, we actually go through all possible states. We have a cycle over all possible states, and we have a max over all possible action at each possible state. That is why we do not have here any problems with exploration exploitation. However, if we do not cycle over all states, but instead sampling some states and choosing some actions, how we choose actions? We choose these actions using argmax from our current estimate of a Q function. So here in this sampling, if we choose some state, we choose action taking argmax not from the optimal function Q, but from our current estimate of a function Q. And this may lead to the situation that you converge to a suboptimal situation. Look at this example with this simple field. So suppose that here in our rewards, we have the situation like the same rewards everywhere 0, 1, -1, and say 0.2 reward here. And this would be, again, the terminal node, terminal state. And you are now state at this position. This is, well, you start from this position, you somehow initialize your V function at each possible position, and you are making actions according to the, not V function, sorry, Q function, and you are choosing actions at each possible position, trying to maximize your current estimate of a Q function. And what you got here, if you stay here, you know that if you go to the right, you would get some positive reward, which is 0.2 times gamma. And if you go to the upwards or to the left, you would get 0. It means that stating here, your Q function on the first iteration would be 0 and 0 for actions upwards and left, and some positive value for going to the right. It means that at the next time moment, you would always, if you are stating in this position, you would always choose the action going to the right. You go to the right, got some positive reward, and stop. This is for sure is not the optimal solution, because the optimal solution is going upwards to this position with a +1 reward. But in order to find this optimal trajectory, you should somehow try these possibly non-optimal actions going in this direction, in that direction, in all possible directions, and possibly in some future, some time horizon, you are able to learn some better policy than if you are going in a greedy way just directly to the right. And that is what is called exploration exploitation. So having current estimate of your Q function or V function, you may try actions according to this Q function, taking argmax of this Q function, and this is corresponds to exploitation regime of interacting with environments, or you may try some other actions that may be not as good due to the current estimate of a QV function, but in the hope that in future it would lead you to a higher values of reward. And in order to learn the good policies, you should somehow balance these two regimes. So you should do exploitation and exploration in the same time during training. And for the case of Q learning, there are two simple strategies how to actually make this, how to solve this exploration-exploitation dilemma. The first method is called the epsilon greedy approach. So in epsilon greedy, the idea is actually very simple. So on the stage of choosing action A in the current state S, you do the following thing. You choose your action according to the current estimate of your Q function with some probability. With probability 1 minus epsilon here. And you choose a random action from all possible set of actions with probability epsilon. So having this epsilon, you either make an exploitation using take an action according to the current estimate of a Q function, or you choose some arbitrary random action regardless the particular Q function. And during the learning algorithm, you may reduce this epsilon value. So you may start with this epsilon value close to 1. So you are trying different actions, you are exploring at a higher rate, and then during learning, your Q function becomes more and more close to the optimal Q function, and you reduce your epsilon in iteration, and finally come to the fully exploitation regime, to the optimal policy pi with the optimal Q function. This is one approach. And the second approach is what is called a Softmax, which is quite similar to the previous one. You use a Softmax function over Q divided by some temperature tau. So here, your current estimate Q function, you use it, but you do not take the argmax here, but you sample your action according to the softmax function from these core values, and depending on the particular temperature here, regulating the temperature, again, you are able to regulate this exploration-exploitation dilemma if your tau is going to plus infinity. So it's big enough. It means that your pi is similar to a uniform distribution. If your tau goes to 0, your pi is close to a deterministic function at argmax position, like this. So again, starting with large enough temperature, then you reduce this temperature during iterations and make this exploration-exploitation dilemma. And the second strategy is, if we compare these two strategies, epsilon greedy and softmax, the second strategy allows you not to do the silly actions. So suppose that at some particular state, you already tried, well, several actions, going to left, to right, etc., and you observe that going in some particular direction is not a good idea. You're, I don't know, following this is the terminal state with some negative reward if you go into the left, for example. So this is not a good idea to do so, and your current estimate of a Q function would be low. And using this softmax allows you not actually to apply the silly functions, the silly actions, the actions for which you already know that it is not a good actions, and look only to the actions with some reasonable values of the Q function. This is the difference between these two strategies, epsilon greedy and softmax. And please note again that this exploration-exploitation dilemma is something that you do not have for the case of a value iteration algorithm, because in value iteration you always do an exploration, because you are trying all possible states and trying all possible actions here. That is why you don't need any kind of exploration-exploitation for the case of value iteration. Okay, today we do not have a seminar because the seminar is getting sick. That is why I proposed for now to make a small time break, like 10 minutes break, and then we will continue with this Q-learning algorithm and consider actually at the place where the deep neural networks are somehow connected with the reinforcement learning algorithm and solve the problem that our set of states can be quite a huge state. So for example, all possible images of a game, and we are just not able to store this Q function as a table function for all possible states and action. Okay, 10 minutes break.